With clean energy becoming more and more popular, many car companies are focusing on constructing more fully electric vehicles. Since these vehicles are operating solely on electric batteries, they are extremely quiet. So quiet that nearby pedestrians are unable to hear an electric vehicle approaching them. This is a serious issue for not only the blind, but also pedestrians who are fully sighted. It was determined that electric vehicles have enough noise above 30 kilometers an hour for someone to hear them. When an electric vehicle is traveling under 30 kilometers an hour, the only noise that can be heard is that of the wheels turning on the asphalt. According to NHTSA, at lower speeds, hybrid and electric vehicles are 37% more likely to hit walkers and 66% more likely to collide with cyclists than traditional gas-powered cars. To fix this problem, the Electric Vehicle Pedestrian Warning System team at Michigan Technological University has created a warning system prototype on a 2016 Ford Focus. Since one of the main goals of electric vehicles is to reduce the urban traffic noise, it is important that the warning sound is both pleasant and quiet. We're currently taking electric vehicles background noise using a Larson Davis sound level meter. The settings for this sound level meter are A-weighted with a fast record time.
So this is the test setup recommended in surface vehicle recommended practices from SAE. So it consists of 3 lines, line AA-, line PP-, and line BB-, which are 10 meters apart. So line AA- signifies the audio recording should start when front plane of the vehicle crosses this line, and the audio recording should stop when the front plane hits line BB-. Also, the sound level meter should be set up on tripods across line PP-. So for taking measurements, we set the vehicle in cruise mode and make it move across line CC-, which signifies the movement axis for vehicle. According to NHTSA, the noise emitted by an electric vehicle should be within 315 to 5000 Hz third octave bands, so it is easily detectable for the persons with no or poor vision. Also, NHTSA requires the pedestrian system to be on as and when the vehicle starts moving, eliminating the control of driver on the system. During literature review, it was found that sound signals with harmonics and amplitude and frequency modulations work best. The signals are easily detectable at low levels. Therefore, we developed a signal which consisted of 9 harmonics of 300 Hz sine wave, and sine and sawtooth modulation was used for frequency modulation and a random modulation for amplitude. The signals were generated using MATLAB and mixed with the amplified noise generated by an electric vehicle at 20 km an hour. The vehicle was then operated with pedestrian warning system equipped, and the sound pressure levels were recorded. The level of the signal was adjusted such that it was slightly audible to the driver when the vehicle was standing.
Get out the way! Get out the way! Get out the way!
Alright, so we're taking a signal from Brett's laptop right here through a cable into an amplifier, and what the amplifier does is it takes power directly from the battery and it amplifies the sound signal and sends it back to the speaker cables onto our speakers up front. We're running all our cables on the outside of the vehicle because this is a temporary setup and we didn't want to drill any holes or poke into the firewall at all. And then as you can see right in here, we have our red lead connecting the power to the battery, and then our speaker cables going down to the speakers. Running 2 4-inch speakers at 30 watts RMS power. This speaker's angled that way, this speaker's angled that way.
After measuring sound pressure level of the vehicle with the pedestrian warning system playing 4 different possible warning signals, the results were compared against the NHTSA standard and the EV and IC engine baselines. On this graph, the NHTSA standard is in red, the electric vehicle is in purple, and the internal combustion engine baseline is in blue. To the right of them are the 4 tested warning signals. At 10 km per hour, the electric vehicle is well below the NHTSA standard in most of the 1/3 octave bands. The signals we developed for the warning system met the NHTSA standard or came very close at low frequencies, but fell short at higher frequencies. However, the equivalent sound pressure level for the generated signals either met the standard or came close to it doing so. These results were consistent with the 20 km an hour test and the 30 km per hour test. Since the equivalent sound pressure levels for the signals were sufficient to meet the standard, but the SPLs in the 2000 to 5000 Hz 1/3 octave bands weren't, the signals can be fine-tuned to raise the SPLs in these 1/3 octave bands and lower them in other areas not specified by the standard, in order to maintain an equivalent SPL that is comfortable to the driver. Despite not fully complying with the NHTSA standard, all 4 warning signals are a significant improvement over the electric vehicle without the warning system, as well as the Hyundai Elantra at 10 km/h.
So after installing the noise system and developing the sound signal to pump through the system, the team sought to produce the quietest possible noise which would meet the NHTSA requirements. And during testing, we brought the signal to the loudest possible level without being able to be detected by the driver inside the vehicle.
In addition to fine-tuning the signal, the next steps for this warning system would be to integrate the vehicle's CAN into the signal generation program so that the volume of the signal matches the vehicle's speed. The current system only has signals for 10, 20, and 30 km/h, but by utilizing vehicle speed data obtained from the CAN, we would be able to create a smooth algorithm for adjusting the signal volume to be adequate at any speed. Additionally, by integrating a noise-canceling system into the vehicle cab sound system, the signal volume could be raised so that it would meet NHTSA standards without adversely affecting driver comfort.